I have been working in automation and controls industry since last 6 years. I have worked in paper and process, automotive at Tesla, and then startup at Heirloom, and now I am part of the boring company where we are digging tunnels underground. In all different roles that I have taken, heavily involved with programmable logic controllers, SCADA, and HMI. That's something I spend my time working on. Today, I'm particularly going to talk about how can we leverage digital twin or virtual commissioning to optimize the new production ramp, or in fact, if we need to revamp any of the factory machines or the manufacturing lines, how could we leverage digital tween to be able to do that? So to start off, I'd like to just provide a brief background on what virtual commissioning is and at what phases of the manufacturing cycle we could leverage or use that. So the main difference between virtual commissioning is something I'm going to point out first. Um, so virtual commissioning is something we use right before we are about to design the manufacturing line itself. And then basically at that point, we need to find out what would be the maximum output coming from the specific manufacturing line, what different way we need to lay out various processes that are required to be able to test the product that we need to make in the on the manufacturing floor. And then in order to do that, mechanical engineers, electrical engineers, controls engineers, and quality engineers, all of this team works together to be able to define those outlines. And uh, at the end, we need to test out the control systems that basically controls the equipment that resides in one manufacturing station or the line, and need to write down software, need to also choose appropriate hardware, and eventually need to figure out a way to be able to integrate hardware with the software by leveraging the programmable logic controllers. So all of that is a bit expensive, and we don't want to directly start buying stuff. In that case, there is an option of leveraging virtual commissioning. So there are multiple simulation softwares which are available in the market, which I'll talk about it briefly. But what those software tools allows us is to do the simulation of how the manufacturing layout is going to look like for any given station that you'd like to model, and then see how a system would behave. You in fact could test out the written code and physically lay out different kind of hardware pieces that would go inside the manufacturing line. And at this phase, you can iron out some of the bugs that you might see in your code. Like for example, here are three different tools or the images you can see. Some of the tools that I have used when I have done the virtual commissioning is Siemens Process Simulate and a Fennec RoboGuide. Emulate 3D is something I haven't used, but it's pretty close to Siemens Process Simulate itself. Um, so as you can see in these images, there is a way for engineers to select where the conveyors are going to be laid out, how long they will be, how far away they'll be from each other. All of this information mostly could basically imported from the predefined CAD or the drawing that mechanical engineer would create it for you, and then you can import that in the software tools. And then so that's a way you know how much spacing need to be in between two conveyors and how the material is going to flow. Let's say if wherever this red tank is, if that's where the material is coming into the system and it's going here on the other station, let's assume that's a tester. So you can pretty much lay out that, and then you can also see how far you need to keep the robot which is picking or placing the parts from the boxes that we can see in the conveyor, and what would happen to the pass parts versus the fail parts. And then in order to write down the process, in order to like automate the processes, the PLC code is mostly written. You can Using the process simulate that is from the Siemens, you can dump the software code to basically test that code out with the simulation system itself. So I'm going to provide particularly one example of like how we end up selecting any one of these tools. Particularly, I end up using Siemens Process Simulate for my system. So I ended up working on one of the testing station, and in which we had to test out the battery cells as they were getting manufactured, and we wanted to see if the jelly roll, which basically holds the electrolyte within the battery cell, if the jelly roll does have any damage inside it, if you're gonna go ahead and fill the electrolyte as a next step, if process or the which has been implemented on that part itself was completely and nicely done before that particular battery cell came to the station that I was working at. So that was just basically the main outline of the project that we had to work on. So there was a multiple way of getting the material to the station, out of the station, and there was some of the processes that were happening at the station itself. So here is the rough layout of how the testing system looked like. So here on the bottom right hand side, there was a conveyor which was bringing the battery cells, and there was a turret which was basically spinning the parts upside down, just because on the one side of the cell we wanted to apply the high voltage to check the conductivity between the jelly doll as well as the battery can. So that process was happening here using the two different testers. And as soon as the battery cell arrived at the station, we wanted to read the barcode on that, just so we can figure it out how many times basically we have performed this test at this particular station, or is this cell does this cell particularly have the correct barcode without any damage. Information like that is something was scanned by that, and that the scanner itself was communicating with the database where we were storing the history of the battery cell as it was getting mass produced. So this battery cells came out of this turret, made its way forward to this conveyor, went straight down here in the tester where the helium jack testing was being performed on the battery cells. Reason that had to do that is just because we wanted to inject helium gas in the jelly roll to see if there is any leak coming out of the roll itself. If there was a leak, which means the jelly roll which was inside the battery cell was not tight enough, and hence the test would fail. And some of the process parameters which supposed to get read as we injected the helium from this small six different stations that you see, that just basically this battery cell had a gantry system that would lift the cells up by like about 2 to 3 inches, would go in some of this system which is shown above, and then the top module will basically inject the helium gas inside to be able to perform the test. At the end of the test, those results were again sent to the database where we wanted to see if the test was accurate, even if it failed, for what reason, things like those. And it was very busy down here on this test table, and as you can see, there could be more number of cells here on the conveyor than this tester could fit on one line. At any given point, tester was capable enough of testing 4 lines of cells that we had here, because there were one machine, or the one part of the machine was capable of handling 2 cells at a time in its subassembly itself. And in order to like think about, when we had to think about like how we're gonna lay out the station, it was not straightforward because we couldn't predict how testing or the manufacturing process of this particular station would look like. So we end up deciding to use the virtual commissioning for this, because of this busyness of this testers here. First, I'll finish how the material exited, and then eventually I'll talk about how virtual commissioning was useful and lifesaver when it comes to like reducing down the commissioning time as well as the cost for us. So once, let's say, the test was done, the material would exit from the outfit conveyor coming out of here, and then some of the battery cells which fail basically the test, which would get rejected here through the actuator, and the rejected part would get kicked out here, as compared to all the good parts would exit through this conveyor and would go to the next manufacturing station. A lot of things going on. We already see three different conveyors to get the material in and out, and one for the reject. Six different stations just to inject the helium gas to test the quality of the jelly dolls, and also high potential testers at the beginning. Things gets pretty complicated pretty fast when you start writing down the code, and if there is no way of like validating some of the test processes, it could basically push down the commissioning time by 1 to 3 months. In our case, it could have gone that long. So we end up taking the virtual commissioning approach in this case. Briefly, the way we had laid down the controls architecture of the testing station looked something like this. We had a main station, which was basically turning all the conveyor on and off by just clicking the start button from the human machine interface HMI. The only thing that wouldn't turn on is will automatically not allow the helium check modules to come down on the cell. They would only come down if there are cells which are not been tested, and we end up storing that information in the PLC as the testing was happening. We'll briefly talked about, I already covered how infid, hypotester, and the helium testers are laid out in the diagram, but there were separate sequences which were controlling each and every conveyors. Like for example, there is no point of running this turret continuously if there is no material coming in. So there were multiple sensors which were overlooking if um, if there are any parts present or not. Like for example, somebody pulls the machine, we don't want to re-perform the high potential test on the battery manufacturing that we were doing at that point. And then same with the helium test, which I covered, that we don't everything whenever the part was introduced to the station, process need to happen exactly one time, unless and until somebody would like to do that manually. And then, yep, I also covered the return conveyor, and then return conveyor and reject conveyor. So where did the virtual commissioning was helpful was most of the time it was more useful here, because we wanted to figure out how long the helium check testing would take place. How do we go about diverting specific number of cells just on the test table? So we had to, earlier there was no divider or the control of the material flow that was going on the table. Whenever we end up writing down the code, which has happened on the side, we end up putting down the CAD schematic of the tester on the process simulate. We end up integrating the PLC system as well as the virtual commissioning tool all in together. And when we were performing the test on the cells, like for example, when they were introduced, they would probably take about 2 to 3 seconds, considering the fact that the speed of the conveyor was about 2 to 300 feet per minute. Test would roughly take about 30 seconds to 45 seconds, depends on if we are doing test for the second time or the material was reintroduced. And um, once the test was done, for how long we'd like to keep requesting the infed material to come to the station. If we do not have any space to store any materials on the table to be able to perform the test, um, in short, that would eventually impact the cycle time of the station. So we had to be strategic about how we requested the input flow, outlet flow, and how fast our testers were. So combination of all those things, you could only learn that when you're testing out your sequences with the physical rather than physical system, but the virtual system, as you're performing the test that would help you evaluate the cycle time of the machine. So that's where the virtual commissioning was much more useful, because we were sending out about 16 parts at a time here versus 32. Earlier, we only had thought about like sending 32 parts rather than 64. So at that time, the cycle time was, let's say, 3 seconds here, 45 here, 10 more seconds here. So it's already over a minute and a half. And the helium check test itself was taking about 40 seconds there as well. So that was about closer to 2 minutes. And then the outlet would add about another 4 seconds or so. So if we didn't have this another two pair of lines down here, if we haven't had added or haven't done the simulation to figure it out, how could we basically increase the cycle time of the station, without virtual commissioning, wouldn't have figured out how we can basically make this table wider to uh, do the test faster, because this test takes about 40 seconds. That's lots of time um, for one material to stay at any particular station. So those are the things that we learned by just doing the simulation. This is one of the example. Now I'd like to move forward and talk about digital twin. So digital twins are mostly useful when the systems are designed on the manufacturing floor and has been performing after some time, and then um, you have figured out uh, a way to produce a part using the station itself. And then all of this data typically get from the physical system, all of the data typically gets sent over to central database, where people could do the real-time monitoring of specific device, how it's performing over the period of time. If one or many of the devices are about to fail, you'd see that, for example, if the motor is running continuously with not having a proper gearbox in between the load and the motor itself, you'd see the current of the motor basically continuously going higher and higher over the span of like a week or so, or maybe months sometimes. Things like those is you can basically derive the insights of the specific devices through the digital twin. And optimization, I end up covering how the cycle time takes place in different scenario, and then what are the ways of like improvising that. This is something you can optimize even after the machines or devices are deployed in the manufacturing floor itself. Um, what kind of systems do we use to be able to derive the data? Mostly proximity sensors. We also can use servo motors that is smart enough to be able to send the data from the PLC to the system. There could be some sort of database which is reading the information from the central database, let's say the manufacturing execution systems, to the physical asset which we are dealing with at any given manufacturing station itself. And if the transaction time between the database, what's actually need to happen on the part which is available at the specific manufacturing line, if that is very high, there are ways of reducing that. If once you analyze it, you can basically see what part of the transaction is taking longer time, things like those. That's where the digital twin comes in place and much more useful. So we have used that in onto the station, which I'm going to provide an example of in a couple seconds. There are multiple tools which are available again in the market. One of my favorite is Siemens MindSphere and Aveva Insight. Pretty much all three tools gives you some sort of data which is telling you for how long a specific part of the motor was running, um, how bad when it comes to availability of the machine, like if some of the devices are faulting more often than the other, it could be due to the faulty logic, it could be due to the faulty hardware. Maybe you need to tune your vision system well, which is looking over the part. The camera has been bumped, things like those. All of these things, if you feed that to the central database, and there is a way of like visualizing that, these are the tools which are useful to be able to make the thing possible. So now I'm gonna talk about the dispensing station where we end up using or leveraging digital twin. So in one cell, down there we had one giant battery pack, mega pack, which is like container sized battery pack, which had three robots in one manufacturing cells. Lots of many things were going between the programmable logic controller and three robots as they were dispensing particularly glue on the on the battery pack itself. Reason that we had to dispense the glue is just because we wanted to keep the pack safe when it was placed outside, let's say under the rain, under the sunlight, things like those. So before the packs got shipped out, we had to ensure that they have proper sealant all across the doors from the top if the rain gets inside. And then there were multiple programming sequences which were happening between PLC and robot to be able to make this dispensing possible. And the goal was to optimize the cycle time and the throughput of the station. This station was already commissioned, but we were not pretty happy with how the cycle time looked, which was little over 1 minute and 40 seconds or 30 seconds, pretty close to that. This is how the layout of the station was. So we had a giant conveyor, and the battery pack was moving from right inside to the left inside as the processes happened. Today, I'm particularly gonna focus on the wherever we see the three robots with the dispensing torch that we see, and the goal of these three robots were to dispense the glue on top of the pack, on the side, just to basically cover if there any gaps between the two metallic frames, um, which were not welded properly, or if they were not manufactured properly, because it's almost impossible to have a zero clearance between two plates. There are always some sort of errors that we need to fix as the part keeps getting produced. So that was just the basic idea behind like why we had to dispense the glue. To be able to command the robot to go ahead and dispense the glue at specific location, we had to rely on the six different cameras that you can see, the small rectangles. Those camera overlook the battery pack and end up finding out if the battery pack was perfectly aligned as this rectangle, or was it tilted little to the right versus little to the left. If uh, whenever that battery pack gets conveyed from the conveyor from the previous station to this station, we don't always get the battery pack laid out exactly the way it looks like in the image. So we need to deal with those real-time scenarios. So for that reason, we had a camera systems to be able to calculate the offset, and those offsets were fed from the manufacturing station, from the PLC's camera to the robots, and then robots eventually end up talking to the dispense system to allow the dispensing happen. And since there were lots of area to cover on the battery pack, the dispense systems that we also had in place sometimes took longer time than anticipated to basically keep requesting the glue. Each and every pack consumed about 3 lbs of the glue because it was container sized battery pack. So there was another challenge of like how do we keep pumping the glue from the station, a third party dispense system that we had, um, from there to the robot. And those are the things we didn't come to know when we were designing the station. We only learned about those as we started dispensing the glue on the pack, and we're continuously analyzing that since this particular station was deployed. Um, so um, first I'm going to talk about how the station's layout was, and where we end up basically missing the fact that that led us to having a lesser or higher, basically, the cycle time. So there was a one parent state machine that was controlling three sub-state machine. When I say state machine, they are capable of starting, stopping, pausing any of the processes that's happening to the sub-assembly or the within the device, within the manufacturing line. For example, uh, this one robot in dispense system would fall under one state machine, because this robot is only talking to this particular glue toad that we have down here. Similarly for the other two, like for example, this dispense station is not communicating with this, so it's okay to have a separate state machine just for this one, and then for the rest of the other two motor robots. um, so that's how the layout was. Mostly was pretty simple. The complicated part was when we had to dispense the glue in between the area. Let's say somewhere in here on this side or the bottom side we have two robots. Let's say if for whatever reason one side of the robot is taking longer time because it's not having enough glue to dispense, then the right hand side robot would take much more time. In that case, we wanted a robot on the left hand side to do more work because it was just available. To be able to analyze those things, we need to have some sort of monitoring system in the background in the PLC, which it did. um, and so when that happens, there would be a handshake that needs to happen between the PLC and robot, just because we don't want this robot to come down here as soon as the glue system is fitting it more glue. So we don't basically, in short, we need to keep the robot safe. Whenever the one enters the collision in a shared zone, the other should not be commanded to come in. um, and in that case, um, not only we need to keep the machine, also the robot safe, we also need to ensure that once this robot has started doing the work, the second one, uh, if we need to basically prioritize to finish some of the task, it's capable of doing that. So overall, it gets pretty complicated pretty
Hey,
fast.
Riddhi,
Mhm.
sorry to interrupt. Just yeah, so just want to make sure that you saw that the low power. Is there? Did you plug in your?
Yep, thank you. Yeah, I'll take care
Yeah,
of it. Yep.
yeah, all right.
Thank you for flagging it.
All right, yeah,
Yep.
thanks.
Hi,
So,
Rishi. I just kind
yep.
of have one question. You can you elaborate a bit more on how the, I guess, robots, how you made sure that they did not interfere with each other? It was it kind of like it's like an open loop control in which one robot does its task, and then once it's done, then
Yep.
the second robot takes over. Okay.
Yep. Sure, I'll cover that.
Okay.
So, this side, left top side of the robot had about seven different tasks. It just
Mm-hmm.
went after one task after the other, and it always happened in a chronological order. As compared to the robot on the left hand side bottom, it had a capability of doing four tasks or three tasks based on availability of the glow system. Same thing with the robot on the right hand side bottom. It could do three or four. The mostly whenever we had to do the task number four, that's when we had to deal with the shared zone between those two robots. So PLC logic continuously monitored um, how which task has been completed, and that PLC was the one which was commanding a specific robot to go ahead and do the specific task at any given point. So let's say if the robot at the bottom, let's say number two, was done doing the task number three, and then the robot on the right hand side, let's say robot number three, had started doing the task from one and two. So we basically pretty much fed the previous cycle times for the each robot for all the tasks. All of those information was getting stored in the PLC,
Hmm.
and at the end of the second task for the robot three, if basically PLC predicted that if it's gonna take the third task is gonna take little over a minute, at that point we would basically allow the robot 4 to go ahead and complete the task. At any given point, if the robot was dispensing the glue where the fourth robot's area was, then robot 3 would not get commanded at all. It would just basically wait for the handshake to come on from the PLC to the robot, from this robot to back to the PLC, and then similarly on this way. That's why we ensure that two of the robots would not collide inside the robot itself.
Okay, gotcha. But in addition to that, there are no other like let's say detection systems on these robots, right? Just to as a kind of like a double precaution, you know.
Oh yes. So another set of layers was that there was a bubble zone drawn around the robot, and then there were also predefined limits. Like just because robot already know their homes whenever they came from the factory.
Mm-hmm.
Um, uh, for example, if we just look at the Cartesian system X, Y, and Z, whenever these robots were moving left to right, and then were making angular position, angular movement from this joint, and then this is where we had end of arm tool to be able to dispense the glue. So we pretty much relied on the Cartesian system. So if the robot is performing task number 3 down here, we do not expect the negative x value to be higher than, let's say, 400. If robot 4 is doing task number 4 down here, then it should not exceed the value of positive x greater than 600, let's say, for example. If any of those, if the particularly the x values go higher than specific limit value, then we'll know that, oh, it could be in the shared zone, apart from the soft logic which was preventing this to robot to come in the shared zone. Similarly, I mean, we also had y and also the theta, alpha, rho, peach, all of those. So those were the values that we were monitoring to prevent the robots to collide.
Okay. All right. Thanks, Riddhi.
Mm-hmm. Go ahead.
Oh no, I just said thank you. Yeah,
Okay,
yeah.
all right, no
Thanks.
worries.
Yeah,
Yep.
yeah.
So yeah, so this is how the layout looked like. But at that point, we didn't have, uh, we didn't account for how unreliable the dispense system could be, and then it was costing us more downtime before we had this the feature of allowing one of the robots to complete the task number 4, excuse me, if the other one wasn't available. um, and we also end up putting, by analyzing the data that were being fed to the manufacturing execution system, we end up basically come up with the idea of like adding the booster pump. The location of the robots also was basically is something we had to move, is just because the glue hoses that we had from the wherever the glue totes was significantly higher, and also we were fighting against the gravity, just because these two robots were mounted about 6.5 feet above from the ground. So um, whatever the pressure that we were applying to the glue system, it was not sufficient enough. So we also end up having not only the boost pump that could increase the pressure from the ground to this system all the way somewhere somewhere at the intermediate location where um, basically the glue could getting pumped to the end of arm tool, and also had one housing down here on the robot to hold some just little bit amount of glue, just so it can continue doing the operations. So these are the things we only came to know after we end up analyzing the data with digital twin that we had stored over like period of 4 to 5 weeks, and then we end up making more hardware changes and software changes, and overall we were able to bring down the cycle time by like 25 seconds, and then that basically went a long way in like keep producing the parts, or at least let them out from this particular station. Um, Upside and downsides of virtual commissioning, as well as the digital twin. In the first example, which I ended up providing about the testing station, we were able to save the commissioning time about like for 2 months to 3 months, just because we came to know that, oh, we might need to make our testing seat table wide enough just so we can feed two more extra lines of the cells, which can also could get tested simultaneously. Overall equipment efficiency, it improved for the hyper tester, particularly where the cycle time was 30 to 40 seconds. If those are the things we only came to know when uh, we were basically ironing out or testing out the programming sequences um, in the virtual environment itself. Lots of bugs gets ironed out in during the virtual commissioning phase. However, it's not 100% because those are the virtual system, not physical system. So I would say about 95% of all the bugs is something you can iron out during the phase of virtual commissioning. Also can stress out the cycle time. Let's say if we feed each and every spot which is open on the manufacturing conveyor, which is feeding the bed. Let's say in the first example, um, the incoming battery cells versus outgoing as well as on the table, um, we would basically find out least amount of cycle time that would machine take. And if even in that case, if we can randomly fault out some of the devices through the virtual commissioning tool to see how we could recover that from the human machine interface, uh, to see how what are the best way to troubleshoot or get the cells out of the systems, just so we can continue the production or we can reperform the test. So those are the things that virtual commissioning tool allows, like fault testing, fault injecting, fault testing some of the devices, test out the recovery procedures or steps that you basically suspect specific test devices to throw at any given point. So these are some of the upsides, and downside is like it's very hard to come up with the first pass yield. It's just because we don't know how many times specific part is gonna fail. Even if you keep reintroducing the same one in the real world system, you'll mostly not reintroduce the same part. If it has failed once in the virtual, uh, people continue doing that. Yep. Any questions?
Yeah. A question. Were all the components that you were working with, were there digital twins for all of these components? Like from the companies where you got these, like the robots from, or the different equipment that did these companies provide, or did they have this digital twin already at hand?
So mostly, for example, Fennec RoboGuide or Process Simulate, those are paid tools. And in per device, they charge a specific amount of like license fees. So
Hmm.
those licenses could be shared amongst all the people. Like mostly, like the system that I work with, people had 5 licenses. I mean, the company had 5 licenses, and multiple engineers worked on that. One of them borrowed when they were working, and then they checked out. But they are most of them are paid.
Okay, gotcha.
Mhm.
And can you also list in the chat box some of I think you mentioned some software, some DT tools that you found useful or you found useful. Do you mind
Yep.
putting that in the chat, please?
Yep. Sure, I'll
That
do
would be
that right now.
useful.
Yep.
Thank you so much.
Yep. No problem. There, I think Fennec RoboGuide has some of the features that it provides has a free version to that. I think Emulate 3D also has some free version. Um, so you could try. I think first Emulate 3D Then Fennec RoboGuide. However, Fennec RoboGuide does not allow us to do the PLC integration with the robotic system. It's more of how you'd like to basically control the robot. Like if you have a CAD, a pre-prepared CAD, you can put it along with the robot. And if you write down in a program in a way where it pretty much performs all the programs that you write, let's say if you're doing pick or place, and you end up importing the CAD of the conveyor as well as one packaging box that you have on top of the conveyor, and you want, for example, let's say the robot to take a picture. So you can write down the code for that just in the Fennec RoboGuide itself. And after that, the calculated vision offset could also reside in that. You can just not send those vision offsets to the PLC system because that connection doesn't exist. But you can still do lots of things. Like once the vision offset has been calculated, you can command the robot to go either on the left hand side versus right hand side based on the calculated vision offset, and it would still complete your robotic sequence that you write it down. Yep.
Thank you, Riddhi.
Yep.
And nice talk.
Yep. No problem.
Yeah, thank you very much for the great talk. Well, one thing that I'm thinking about is I know NVIDIA is also working on this kind of stuff, like digital twins. I think they call it world foundation models. So are you aware of their tools? Like how does it compare to the ones you use here, like from Siemens or other companies?
Mm-hmm. Mostly in manufacturing sites or machineries, I feel like companies are still a bit hesitant with like integrating AI tools when it comes to like use deploying that on industrial robots. Reason is that people people's lives is at risk. Most of the robotic sequences that we use are mostly tested um, beforehand, before actually robots start picking, placing, welding, all different kind of application that it's capable of doing. um, those programming sequences, like as of now, more than 98% of the time is written by an engineer and has been validated by an engineer. When it comes to using the AI and ML for the cameras, to detect the part, I think I see engineers are much more open to adopt those technologies there. Like for example, the barcode scanners that we had, which we had to read on the battery cell, the ML ended up playing a huge role in getting the reliability rate closer to like 99%. So really game changer. Before that, it was like 78, 79%. So that was like a 20% of jump. Basically what how ML and AI end up enabling, or basically end up predicting what would be the missing piece of barcode, and provided us the accurate information almost all of the time. Like the error was 1%. So things like those where I've seen ML and different kind of models being used more openly.
All right, thank you so much. Any other questions from the floor? I noticed there's one person who just joined, but it's okay. We'll upload this talk to our TC website, so feel free to check it out.
Yep, feel free to also reach out to me. If you have any question, I can share my LinkedIn here, or email ID. I'll share both. I didn't particularly get trained on how to develop automated system when I was in college, so I might have talked about some high level stuff. If you want me to simplify something for some of the projects that you might be working on, I'm happy to do that as well. So feel free to reach out.
Okay.
Yep. So I shared my LinkedIn as well as the email ID.
Yeah, sure. Great. Any other questions? So if not, let's thank our speaker. Thank you so much for the great talk.
Thank
Very
you.
exciting.
Thank you, everyone, for coming. And yep, happy to help. Just reach out.
Yeah,
Cool. Thanks
sure.
again.
Yep. Thanks.
All
Bye.
right.
Bye.
Yeah, thank you. Thank you so much.
Yep.
Bye.
Yeah. Thank you.
Thank you.
Yeah.